Good morning. I'm just going to quickly go over some things dealing with the linear regression analysis. So this is like finding a best fit curve. Actually, I should just say finding the best fit line. In this intro stats course, we're just doing lines, so finding the best fit line. You could do parabolas, cubics, exponentials, logs. You could do regression analysis with other curves. We're just using straight lines though. When you find the best fit line, we call that in this class the least squares regression line. And I'll explain how that works in just a second, just so that you understand it. Your calculator will calculate the equation of the line for you. So all you have to do is enter in your data, and there is a video in the YouTube playlist, not made by me, but that does go over how to use your TI-84 to compute the best fit line equation. So that's fairly easy. I'll quickly run through things that you can do with a calculator, but you should watch that video for step-by-step instructions for how to actually compute the equation of the line. I just want to give you an overview of what it's doing and how to interpret certain values that you get. So let me switch over here. There we go. All right, hopefully you can see my screen. This is, again, what we call the least squares regression line. Where's my drawing pen? Oh, there it is. What that means is, let's say I've got some lines with some data. I'll try to do a couple of the same, almost the same. Something like that. So I can draw in some lines here. I'll do blue, I guess. There's a line. There's a line. There's a line. Those are some examples of lines that you could draw. I'll do another. And then maybe we'll also draw this line. So if I labeled these A, B, C, D, which would be the best fit? It's pretty clear, I think, hopefully, that you can tell that A and B are not very good fits. C and D are much better, but how do you know which is the best of the two? Yeah, now of course I didn't draw the dots exactly the same. I guess I could overlap them. So let me draw like a green line. What if I did a line like this or a line like this? Especially in D here, now that you have the blue and the green line, which of those is the best fit? It may not be the easiest thing to tell. C could also give you some difficulty. Which is the best fit? What really defines the best fit? It's not just eyeballing it. There's a mathematical specification of what the unique best fit line happens to be. And it has to do with what we call residuals. So the idea here is that, okay, let's say there's a relationship between, whoops, it's not normal, a relationship between one variable and another. So let's say there's a relationship between X, maybe that's your height, and Y, your weight. So typically the taller you are, the heavier you are. So according to our model, those are related. So the taller you get, if you're at 0 height, you're at 0 weight. And as you go up, As your height goes up, your weight also goes up, and it's proportional. So that means it's a line that crosses through the origin if it's proportional. That's from Algebra 1, maybe. So if you have a proportionality between two variables, that means they go up like a line, and they cross. There's zero, one is zero, and the other is zero. Let's say that's the model. That the taller you get, the heavier you are. That's a model, and the line specifies. Sometimes we call it the signal through the noise. So, like, imagine you're trying to, like it's what is it, 1969? People are, moon landing thing. We're trying to get video signal back to the Earth. There is the signal, and then there's noise. So you're getting a sort of image, but it's a little staticky. Pixels, if you want to call them that, are kind of all over the place. There's some shape to it, but it's losing some shape. It's kind of a little bit mixed up, not fully mixed up, not totally randomized, but a little messy, a little noisy, but you can still see something like an image. So we talk about the signal versus the noise. And a lot of times when you're dealing with real world data, like let's say someone lost a leg. Okay, so sure, they're taller, but maybe they weigh a little bit less than someone who's slightly shorter, but with both legs, and therefore they break the model a little bit. They're taller, but they're not as heavy because they're missing limbs. Or you could have someone who's short and extremely obese, and they might be heavy even though they're short. You could have a very tall person with thin bones and very lanky, who's a lot lighter than someone who's shorter and muscular. So there's some randomness, there's some things that don't fit the model, that don't fit the relationship between the variables that the model presupposes. In that case, the data may sort of form a line when you plot it in a scatter plot, but not exactly. There's little things are a little bit off. So the model represents what we imagine to be the signal. We believe that there might be a relationship between the variables, a linear relationship, but there's going to be some noise. So the question is the noise, does it seem like the noise is what we would expect from randomness alone, or is the model not a good fit for the data? So where's that cutoff? So the way the best fit line curve works is that, how do we know a line is bad? Well, we draw what are called residuals. So if I go to this x value, the model says the value should be here, the actual value is here. So the residual, what we call the residual, is the difference there. So we have a large negative residual at that, let's call it x equals 1. So at x equals 1, we have a large negative residual. At x equals, I don't know, 7, I don't know, you got an even larger negative residual, another negative residual, a positive residual, a negative residual, and a large positive residual. So those kind of like branches of a tree, they're long, they're little hairs that stick off of the line vertically. So it looks like it's perpendicular to the line, the model that we've drawn, but it's actually just vertical because it's at that particular input value, that particular value of x. So we're looking at residuals that way. B is also not very good. I have large residuals, negative here, negative here, negative here, negative here, positive here, positive here. So large residuals, not exactly the best fit line for that data. All right, so which is better for C, the green one or the blue one? I'll do the blue one here. So I've got a positive residual, a negative residual, very small positive, a negative, small negative, almost non-existent negative. Much smaller branches, like if I put all my branches together from these 3 lines that I've done, C is definitely the shortest length if I put them all together. That's telling me that is better than A or B. If I do D, almost nothing, something, something. So it looks like D might be a little bit better. The blue line in D might be a little bit better than C. So what the best fit line is really doing is it's minimizing those hairs. And it doesn't matter if they're positive or negative. Any length is considered bad. It's just minimizing those in principle. That's the principle for selecting. That's the selection principle for what is the best fit line. We call this the least squares method. Really, because if this is a positive residual, this is a positive, this is a negative, and I guess that's a negative and a positive. Any length, I don't want to have, like if you look at B here, I've got some negatives and I got some positives. Well, if I just add those together as positives and negatives, there's going to be some cancellation. And so if I had this, or if I had, if they cancel, then I can't distinguish things that are very spread out from the line, but balanced for positive and negative, versus things that are very tight to the line. So in order to distinguish that, we don't care about the sign of the residual. We just want to take the length. And when you want length, you typically just square the values. So what we do is we look at this difference, we square that difference. So when you square a number, it always becomes positive. And then we kind of average that, and we get what's called an R squared value from those calculations. That's called the coefficient of determination. And then the correlation coefficient is the square root of that. So we kind of go back to something that, rather than the square of the distances added up, it's now more like the distances added up. So first we square the distances of the residuals to remove the sign, or to make them all positive. Then we kind of average those. And then that, if you leave it squared, if you have something that's related to the square of the distance of all those hairs put together, that's the R squared. And then if you have something more related to the distance itself put together, ignoring the sign, that's called just R, Pearson R coefficient. And that's called the coefficient of correlation. So what the least squares method is doing is finding the line with the minimum hairs, basically. That's what it's doing mathematically. Your calculator can do that for you. You don't have to do that. You just put your data into your calculator and you press calculate and you write down your answer. That's all you have to do, really. So it's fairly easy. It's just important to understand what in principle it is. What does it mean? What is it doing? So you have, that's just stuff to be familiar with. Okay, now with any set of data, you can calculate the best fit line. The question is, should you use it or not? Should you use that as the model? Is there a signal through the noise, or is there so much noise that the signal's unreliable? If there's too much noise, you may calculate a best fit line, but like for instance, okay, is it this? Is it this? Is it this? Who knows? Who cares? There's so little relationship between changes in one variable versus changes in another. It doesn't matter. So what we're talking about here is correlation. How do you even spell that? What does that mean? Well, how is X related to Y? Are they related? What we mean by that is, if I change X, will Y change? And how so? So here's what we have. Here's some examples of different correlation coefficients. Here they're using rho, the Greek letter R. It looks like a P, but without a little stem here. It's just kind of like you start from the bottom and you kind of go up in a loop, and it just makes rho, the Greek letter rho, lowercase. And if your data, here's some examples here. Here's a very tight fit. All your data fits on a line. We have a correlation of 1, like 100% correlation. Here is, you can definitely tell as you increase X, you increase Y. So as X goes up, Y goes up. There's some noise in that signal, but it's clearly a line. So that's like an 80% correlation, and it's positive because it is a positive slope. Here is a weaker correlation. If you have lots of data, a weak correlation is strong enough to prove the relationship. If you only got a few data points, you really need a strong fit in order in order to trust that. But if you have tons of data, like this cloud here, even a weak correlation or a lower correlation coefficient is enough to establish, that's enough evidence to establish a correlation. So in this scatter plot, you can definitely tell that as you go right, it goes up as well. So that's another positive, but not as strong correlation. It becomes negative when you go up in one variable and the other goes down. So it's like inverse relationship there. So but again, the tighter it is, the more it goes to -1 in this case instead of a 1. So 1 is a very strong, tight fit correlation between X and Y, where they go hand in hand. Increase one variable, you increase the other. A -1 is a very strong, very tight fit to the line when, as you increase one variable, you actually decrease the other variable. And you can have weaker correlations in both trends. If there's no clear relationship, if it's very, 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 very noisy, that is a 0 correlation. Now it has nothing to do with the slope. It has to do with the fit, really. It has a little bit to do with the slope. So here is positive, positive, positive. Here it's negative, 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 because as one goes up, the other goes down, versus on this side where one goes up, the other goes up. But the number really has to do with how strong the fit is of the model, and versus how if you have not very big residuals, if it's a perfect fit, you have ones or -1s. And if you got some noise in the signal, it's less. It's not quite 1. The absolute value is not quite 1. Now, this looks like a really good fit, but you'll notice that as I take X up or as I go down on X, Y is flat. So Y does not change as you vary X. So if I go for someone who's really, 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 really tall or someone who's really, 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 really short, they weigh the same. Doesn't matter. So even though it's a tight fit in that case, there's no correlation. The height is not correlated. There's no real relationship between the height and the weight according to this data in the middle here, because as I make one go up or down, the other one doesn't notice. So even though that's a tight fit, there's no correlation there. Correlation is not just about the fit. It's also about the slope to some extent. Really, if it's flat, there's no correlation. If it's anything other than flat, you could have correlation. Also, when we're talking about linear correlation, especially, like all of these models would be no correlation. Anyway, so you're going to have some questions like which one has this coefficient, which one has this coefficient. Hopefully those are simple for you. When you're asked to calculate the best fit line, how do you calculate the line that fits the data? Let's see if I can pull that up real quick. I gotta go to my downloads folder. Boom. Wabbit. Boom. I gotta browse for my TI 84 RAM. Finish. Okay. Boom. Boom. Okay. So, how do you get the best fit line? Well, you go to stats and you edit a list. And in one column, I'll do, 5, 6, 11, 14. Okay, and on here I'll do 1, 2, 3, 4. Actually, I did that wrong. I want to do, I want to flip those actually. So I'm going to do 1, 2, 3, 4 here. And over here, I'm going to do 5, 7, 6, 12, something. Okay, so let's say, so if I have a point like 1, 5, 2, 7, 3, 6, so I've got dots, I got coordinates on my scatter plot. I would put the x values here and the corresponding y values for each point here. So each one of these rows represents xy point. They represent coordinates. I think you could go to stat plot to test that. Anyway, you put in your data, you put in your scatter points. Now I have 4 data points. If I had to look up my degrees of freedom, it's always 1 less than the number of points I have. So I'd have 3 degrees of freedom if I have 4 data points. How do I calculate my best fit line? Well, for one thing, you may need to go to your catalog if you haven't activated this yet. And you might want to, you won't get as much information as you need unless you go down to, in your catalog, find diagnostics on, and then click go, and then press enter again to run that program. And then it turns on features that your calculator has, but for some reason doesn't use until you tell it. So your calculator can do stuff, but it won't unless you tell it to actually do everything it can do. I don't know why this comes off by default, but it stupidly does. So turn it on. And then once you get your data entered, you go to stats, calc, linear regression. Instead of y equals mx plus b, it's going to say y is equal to ax plus b. So let's get our best fit line using our data. My x list is L1, my y list is L2. I could store this into the y1 variable if I wanted to plot it. You don't have to, you could leave that blank. And there we go. My slope is 2, my y-intercept is 2.5, my correlation coefficient R. These two values here are what you need to turn on. When you turn on diagnostics, you get these. My correlation coefficient is 0.83, and I could plot it if I wanted to, but that's usually what I need. So if you need your linear function, it is y equals 2x plus 2.5. That's my equation of the best fit line. And then you may be asked, is there a correlation? Well, because the slope is positive, if there is a correlation, it would be a positive correlation. So as x goes up, y goes up, because the slope is 2. But whether or not we have strong enough of a fit for this number of data points, I need to check to see if 0.83 is a strong enough correlation. So my data has a 0.83 correlation. You would usually have a table of some sort. So here I'm going to go with, which one do I normally use? I think maybe the 95. I don't remember if it's 95 or 91 that I use normally. It doesn't really matter. You pick a level of confidence that you want. So if you wanted a 95% confidence or a 99% confidence, you choose one of those levels. Usually it will, if I gave you an assignment, it would normally have a table given to you. And then it either will give you the number of data points or one less than that. This is the degrees of freedom. So I had 4 data points, I believe, which means I had 3 degrees of freedom. So let's say I was going to go with the 5% significance level. So my threshold, and because that's such a small number of data points, I would need to have a correlation closer to 1. It doesn't matter positive and negative. We're just talking about the absolute value. But my correlation coefficient would have to be closer to 1 or negative 1, if I just look at the absolute value, than 0.878. Mine was 0.83. So this is not as close to 1 or -1 as this. So even though it's a pretty good fit, with only 3 data points, I can't trust it as much. I need a better number than that even. So even though it's a pretty good fit, because I have so few points, I can't say that that I can confidently say that there's correlation. I would need even better, or I need more data points. But if there were correlation, it'd be positive. I'm pretty close, but I don't have it. So I can calculate my best fit line. Is there a correlation? No. No, there's not. I didn't get it. So in order to say if there's correlation or not, you'd have to compare this to a list. Compare your R value. I don't think the assignment that you have asks us to do that, but that's what you would do. That's all that's involved. You just check your R value, look it up, and see if it's strong enough. And if it's not, you don't have it. If it is, at least at that confidence level, and if it is strong enough, you just see, oh, is my R positive or negative, or is my slope positive or negative? Since these are positive, if I did have it, let's say this was 0.89, then I would be strong enough and I could say I have a positive correlation, but I don't have it here. So anyway, I hope that makes some sense. I just wanted to explain what this regression method does, how to do it with the calculator. Check out that video for a better walkthrough than what I just did. And when you want to see if that's a good enough fit or not, you can always get the equation, but can you trust the equation? That comes down to that R value and checking against the table to see if it's a strong enough correlation given the amount of data that you have to trust it. So I hope that makes sense, and that's what you have for today. So have a great day. There we go.